Afternoon, folks. My name is Eric. I'm with the AWS security team, and today we are here to talk about a very exciting topic, encryption. I tried to keep the title theme going, but I think I have to admit that Dickens is better at this than I am. This is not a sales talk. If you wind up using more AWS services, more of our encryption features as a result of this talk, that's great. But if you leave here and you take deeper ownership of your encryption, and you better understand the questions you need to ask and the things that you need to understand when you use encryption, that's great too. This talk is about some of the challenges that we've run into within Amazon and within AWS using encryption. And in many cases, the answers to these challenges are visible in our services. So at a high level, you have data. Your data is precious. You want to protect it. And when we think about protecting digital data, we always say encrypt it. That's Fort Knox. James Bond made that globally famous. Why do we encrypt? And often our encryption conversations with our customers start with compliance. PCI DSS is prescriptive. HIPAA is also prescriptive. In fact, HIPAA losses can go from millions of dollars to not even reportable if you're using encryption correctly. I asked our compliance team, and I say this with all seriousness, our compliance team is awesome. I never thought I would say awesome compliance team out loud and really mean it, but our compliance team is awesome. For a sample of the controls that mandated encryption, that discussed encryption, I got back a 7-page document. There's a reason that all of these compliance regimes talk about encryption. And the reason is that it's actually a very powerful control for managing access to your data, for maintaining control of your data. But encryption is hard. You're thinking like, what do you mean it's hard? Like these algorithms are well known, and the software is free, it's built into everything. Like how could it possibly be hard? It's also expensive. What do you mean expensive? Like Intel has ASNI, it's built into the chips. My phone encrypts every bit written to persistent storage, and it's not a James Bond phone. I bought it at the store, it's a commodity device. So how is encryption expensive? The net result is, despite being hard, and despite being expensive, encryption is sometimes worth it. I'm not telling you not to encrypt your data. You just need to understand what you're doing and when to encrypt your data. So we've got a simple recipe here. You take your data, you add a key, you mix it together using math, and the result is ciphertext. The ciphertext is effectively noise. It should be uncompressible, high entropy, indistinguishable from random. For all good crypto, the math is public. Anyone can go to the store, they can buy a blender that looks exactly like your blender and works exactly like your blender. The security of the system relies on the secrecy of the keys, not on the secrecy of the math. Our analogy breaks down. You can't unmake a cookie. You can't turn it back into an egg. But in order for encryption to be useful, it has to be a reversible process. You have to be able to put in the ciphertext and the key and some math, and you have to be able to extract the plain text again. Now this simple recipe, this model of encryption, implies that failures are going to be Boolean. That is, either you have the ingredients and you can get back the plain text, or you don't. So back when I was young and stupid, this is how I thought crypto failed. It's not a little bit cracked, that window is shattered. Either it's gonna be okay, or it's completely broken and totally not okay. I was much happier when this was my mental model of encryption. The reality is much closer to erosion. Like, no engineer is gonna look at that road and say it's okay. But it's not completely gone. Like maybe if you stuck to the right, it's still passable. I bet that a month ago this road looked fine, and I bet that a month from now, Evel Knievel wouldn't be able to pass it. And so there's a gray area in there. At one point, this went from being a road to being a disaster area, but it's not like there was a moment when that was eminently clear. People can disagree on when it's no longer advisable to use this road. So to see how that can happen, we're gonna have to build a stack here. The basic building block in cryptography is a primitive, a cryptographic primitive. So I've got a super secret message, and we're going to use a block cipher. A block cipher is a commonly used cryptographic primitive. This is the fundamental building block of cryptography. And because I didn't like building boxes in PowerPoint, it's an 8-byte block. So the first thing we do is we chop our message up into 8-byte blocks. And we take one block of this message, we feed it into the block cipher with the key, and we get out encrypted ciphertext. It's glorious. This works. The problem is we haven't encrypted the entire super secret message. We've just got super C, which isn't enough. So we can just repeat this process. And we can keep doing this forever until we've consumed the entire message. So the block cipher is a primitive. It's a cryptographic building block. And what I just described here, where you take successive blocks of the cipher of the plaintext and encrypt them, that's ECB, electronic codebook. That's a mode of using a block cipher. And then these things get stacked together into protocols. And we're on the internet, so TLS is the most common cryptographic protocol that we all touch. And it's usually a conversation between Alice and Bob, but I'm going to use a conversation that's closer to home. I could not find a logo for the Bodo SDK, so this is the Python logo. And I was able to find a logo for AWS, of course. And we want to have a secure conversation between Bodo and AWS across an arbitrarily bad network. And when I say arbitrarily bad, I mean you can think of any bad thing that can happen to that network traffic, and it can happen on this network. So someone can look at your packets. You want confidentiality. Someone can reroute your packets. They can send them somewhere else. You want to make sure that you're actually talking to AWS. You need server authentication. Maybe the packets are going to go where they want, where they're supposed to go, and they can't be snooped, but they can be altered. They can be mangled in flight and have unintended consequences. You want to be able to tell if the packets have been altered. Maybe I have no idea what it is that you're sending, but I observe that after this particular message crosses the network, an EC2 instance is terminated. I wrote that message down. I can just keep pushing that through the network and terminate more instances. You want to have replay protection. There's a whole bunch of goals that TLS as a protocol has, and that block cipher only gets us confidentiality. So we're going to have a whole bunch of these. To see how we can have these non-Boolean failures, we've got a recipe here. This time I'm going to encrypt a different secret message. It's awfully, awfully secret. It's not super secret this time. We're going to take the block cipher, we're going to chop our message up into blocks, we're going to feed a block into the block cipher, and we're going to get out a block of encrypted ciphertext. Everything is working fine thus far. We're going to do this again, and we're going to do this again until we exceed the entire message length. The problem here is the encryption is deterministic. My first two blocks of plaintext were the same, which means that my first two blocks of ciphertext are the same as well. I've leaked the fact that the first two blocks of plaintext were identical. You might think, this is a tiny little leak. You know, it's not that bad. I don't need to worry about it. This is Tux the Penguin. I'm sure you've all seen him. This is Tux the Penguin encrypted with ECB. I haven't broken the encryption. I don't have the key. The block cipher is still intact. I don't actually know what the plaintext message was. But I'm pretty sure I know what the plaintext message was, and whatever goals you had in encrypting this image, you did not achieve. And so this is a non-Boolean failure. Often the obvious construction is very broken, and often for very subtle and non-obvious reasons. And so the bottom line here is that cryptography is not for amateurs. You need to deeply understand what it is you're doing with your cryptography and what guarantees it's providing you. The block cipher here did exactly what it claimed to do. It was the construction, it was ECB, that didn't deliver. And so we're going to have our primitive, we're going to use it in some mode, it's going to be a part of some protocol, but again, TLS had all of those goals. And so there's going to be multiple primitives used in multiple modes, and the protocol has to span all of them. And so each of these blocks can have problems, and the junctures between each of these blocks can have problems. There's a lot of opportunities for complexity and a lot of opportunities for flaws. And so much of modern cryptography is based on these two words. Cryptography is a weird, weird science. It is very rigorous. There's a ton of very foundational math involved. We have smart people that work on these things for years, and we don't find any flaws with them. And we publish them, and they make it out into the world. It takes about a decade for new crypto to get into widespread use. That's a lot of time for a lot of people to look at it, and we believe that it's secure. And then some smart, creative person has a new idea, and they say something that's never been said before, at least never been said publicly before, and our beliefs change and our world shifts. The two places that people tend to use cryptography are on the network and at rest. That picture there on the left is an actual data center that I used to work in, but it is not an Amazon facility. So we'll start with encryption on the network. In the modern internet, encryption on the network almost always means TLS, so we'll talk about TLS. And we're going to start with a tale of one cipher, RC4. RC4 is not a block cipher. RC4 is a stream cipher. With a stream cipher, you take your message, and you're going to feed it through the stream cipher, but it's a stream. It streams bytes. It doesn't use blocks. So you chop your message up into individual characters, individual bytes. You feed the key into the stream cipher, and the stream cipher generates a series of key stream bytes. And this is a potentially infinite series, and you should stop using it at some point, but I ran out of room on the slide before we hit that point. And then you do a byte-wise XOR between your message and the key stream bytes, and that gives you the encrypted ciphertext. So this is a generic diagram for all stream ciphers, but RC4 in particular is the stream cipher we're talking about. RC4 was written by Ron Rivest at RSA in '87 as a trade secret. It was not publicly documented, and as a result, it wasn't patented. So a few years later, it was anonymously leaked. It showed up on Usenet because that's how we communicated back then. And it's fast, and it's not encumbered with patents. So it very quickly got included in SSL, and then when SSL turned into TLS and was formalized, it was included in TLS. And at this point, it's a thing. There's a whole bunch of ciphers that are supported by TLS, and you can use RC4, whatever, it's there. And then in September of 2011, this paper was published. It's a good paper, you should read it. I think this might have been the start of the clever names for vulnerabilities. In order to understand what this paper is talking about, we need to go back to a little bit of crypto. When used with TLS, at least back in the day, block ciphers use something called CBC, cipher block chaining. It's another mode of using a block cipher. Instead of ECB, you use CBC. And again, we've got our awfully secret message. We've got a block cipher. We're going to chop it up into blocks. We're going to feed them into the block cipher. But this time, before we do that, we're going to take an initialization vector, an IV, and we're going to XOR that into the plaintext before we feed it to the block cipher. The initialization vector doesn't have to be kept secret. In TLS, it goes on the wire. It's visible to the attacker. But it can't be controlled by the attacker. That's the constraint. And so we do this, and we get out some encrypted ciphertext. Before we do the next encryption, we take that last block of ciphertext, and we XOR it in to the next block of plaintext. And so this way, every block, we're scrambling the encryption. We're injecting this initialization vector as new state. And that means that even though we've encrypted the same plaintext block twice, we're not going to get the same ciphertext block out twice. At least not without a 2 to the 128 chance or whatever. So that's great. There is a well-known attack against CBC. It's called the chosen plaintext attack. In the chosen plaintext attack, we're playing a game. We use, in this case, we're going to use a browser. Maybe I've injected some malicious JavaScript. So I can propose messages to be sent. I can cause the client to send the messages. I can observe the resulting ciphertext. I'm using the holder of the key as an encryption oracle. I get to choose the plaintext. I get to see what comes out the other end. I don't get access to the key. So this equation here is exactly the same as the diagram I just drew. So a given block of ciphertext is the previous ciphertext block encrypted with a plaintext block, all encrypted using AES under a key K. As a reminder, if you XOR a value twice, it's a no-op. And what we want to do is we want to decrypt C sub I, obtaining P sub I. We want to break the encryption. And so we're going to pick M. This is our guess. This is the message that we think is actually P sub I. And we're going to give it this particular form. These three values XORed together, and we're going to hand that to the encryption oracle, to the user's browser, and we're going to have them transmit it. And what they're going to do is they're going to take C sub j minus 1, the previous block that they just sent, wherever they are in the chain. They're going to XOR it with the message we just gave them. They're going to encrypt it, and they're going to send it. But the message we just sent has that particular form. There's two C sub j minus 1s in there. They XOR out. And so by picking this peculiar form for this message, we've managed to swap out the value that was used to scramble the encryption with the one that was used to scramble the encryption for the block that we want to decrypt. And so if the two ciphertexts match, if the ciphertext of the message that we want to decrypt matches the ciphertext for our guess in this particular form, we win. We've won the game. We've guessed the plaintext. We haven't gotten the key or anything like that. But this is a really, really slim attack. I'm guessing an entire block. AES uses a 16-byte block. So I'm guessing in a 16-byte space, 128-bit space, and I'm doing it through this game with the encryption oracle, observing traffic on the network. It's a very slow game. And so it's not a real-world attack. It's just a known attack on CBC. This is the kind of thing that cryptographers spend their time on. What the paper introduces is the Blockwise chosen boundary attack. And this is clever. These are smart guys. In order for this to work, there has to be a field that's repeated, that's worth stealing. And in the web world, those are cookies. When I get your cookies, I put them in my browser, I'm you. And there has to be a field where we can control the length. And with JavaScript, that's easy. It's the path. And so we're going to chop this up into 16-byte blocks. AES uses a 16-byte block size. And we're going to extend the length of the field we control until there's only 1 byte of the value that we're guessing inside the block. The rest of that block is HTTP headers. I know what they are. Like I can do this myself on my own desktop and send the request and look at what the headers look like. And so I guess A for the one unknown character, and it's wrong. And I guess B, and it's wrong. And eventually I'm going to guess capital S, and it's right. So I've guessed 1 character of this block. We shorten the value that we control, we pull a second byte into the block, and the guessing game starts over. And I just keep repeating this character by character until I've extracted the value that I'm interested in. The cookie that we're interested in extracting is a full block. I put this number up here because I could. It barely fits on the slide. That many guesses is what is officially known as a lot. Two to the 8 is the full ASCII 8-bit character space. In reality, you wouldn't have to guess 2 to the 8 because no one's going to have a cookie that has unprintable characters in it. But at worst case, we're talking about 2 to the 12th, 4096. This is the kind of latency improvement that as computer engineers we all dream about. Have you ever made anything in your life 2 to the 116 times faster? The Blockwise chosen boundary attack takes the chosen plaintext attack from a theoretical curiosity to something that can actually be executed in the real world. Now, there's a lot of caveats here. This is a complicated attack. I need to be able to make your client make requests. I need to be able to perform the encryption oracle guessing game. I need to be able to control the block alignment so I can guess character at a time and pull extra characters in. I need to be able to see the resulting TLS traffic. And there needs to be a field that's worth stealing. But if all those are true, I can perform this attack. And so this is another great example of a non-Boolean failure of crypto. This is a real-world attack. You can actually perform this in the real world. And all those stupid movies with the encryption breaking thermometer, like that actually applies here. The attack takes several minutes and tens of thousands of requests. And so maybe the movies got it right. But this actually can happen in the real world. And so when Beast was published, everyone flocked to RC4. It's a stream cipher. It's not a block cipher. It's immune to Beast. And so it's gone from to use it. But this is AWS we're talking about here. Every time we've made changes to the TLS config on our API endpoints, strange things have happened. You change TLS cautiously and carefully because it's a protocol that's used between arbitrary clients across the open internet. You don't control these implementations. You have no idea what these people are using. Some of that code was originally carved out on stone tablets. And you can't call up the internet and say, would you please upgrade? And so you want to make these changes deliberately. First of all, most AWS API clients don't have JavaScript in them. There is no way for the attacker to inject code. But even if you are using your browser as an AWS API client, we don't use cookies. There's no repeated value that's worth stealing. This is stolen from the AWS documentation. This is the procedure for generating an API request signature. And it draws on request elements. So each request is going to get a unique signature, and one of the request elements that we sign is the timestamp. And so even if you've got a client that's sending the same request over and over and over again, that signature is going to change. There's nothing that you can do. You can't play the encryption oracle guessing game against an AWS API endpoint. So we actually left RC4 enabled to avoid upheaval for our clients. This kind of request signing isn't the kind of thing that you can push quickly through the RFC process in the general browser world, but it is the kind of thing that we could do with our API endpoints. And when we built it, we thought of it as crypto insurance. It wasn't something we needed at the time, but we thought it might be useful in the future. And then the Beast was one of several CBC attacks that started coming out, and our crypto insurance policy paid off. These attacks just plain didn't apply to our APIs. So then, in 2013, a couple of years later, there was a paper out of Royal Holloway. Part of the internal state of RC4 that I didn't talk about is the key schedule. It's 256 bytes of stuff that's calculated in a fairly straightforward way. In an ideal world, in a perfect stream cipher, this would be truly evenly distributed. So this is a graph of the values that were observed for the 33rd byte of the key schedule. And in a perfect world, this would be a flat line at 1.0. This is not a flat line at 1.0. And so this is showing that statistically, the RC4 cipher is flawed. This was the beginning of the end for RC4. This is hardcore crypto research. And so they showed the statistical biases, and then a couple years later, it was pulled from TLS. It was officially removed. And so then, it was like, dear Lord, don't use RC4. So in the space of a couple years, it went from a thing you had to a thing that you absolutely should use to a thing that you absolutely should not use. But of course, changing TLS, we left RC4 enabled on some of our API endpoints, and we give our customers the ability to enable RC4 because of things like televisions. These are embedded devices, and it's not your toast is ready, or your lights are on, or what temperature do you want it to be at home. This is streaming HD video at 60 frames a second. If the device doesn't stream video at 60 frames a second, it is useless. It is a paperweight. And we're talking about DVRs, streaming sticks, televisions themselves. It's not like a guy is going to show up at your doorstep with an upgraded processor. And so the way the TLS handshake works is the client reaches out and it says, these are the things I like. And they come in order. And then the server gets to pick one of them. And so RC4 is broken, we'll pick AES. It's the next one in the list. AES is a great choice. The problem is that the device can do AES and 3DES, but it doesn't have the CPU horsepower to stream 60 frames per second HD video using AES or 3DES. So it works, but it doesn't actually work. Like in a mathematical sense, it's functional, but in a consumer sense, it's useless. And so it's lying to us. And there's nothing we can do here. So if you own a video streaming service and these are devices that your customers are using, you have to make a business decision. And you have to understand the risks involved and whether or not it is worth it to leave RC4 enabled or to disable it. We have one team within AWS that does this stuff. I don't know if you've done any of the AWS culture talks or anything like that. It is very unusual to centralize things at Amazon, and this is one of the things that we centralize. This was in, I think, Andy's slides yesterday. There's no compression algorithm for experience. We have people that are deeply embedded in the RFCs, in the community. They know what's going on, and they understand deeply the crypto involved here. And even at AWS's scale, we have one team that does this because we don't want to pay to build that up twice. This is a screenshot of the ELB console. And I have selected the latest security policy, and this is, I would like the crypto people at AWS to make some decisions that are likely correct for me. And this is a great choice, we use it all the time. But if it's not the right choice for you, this is why you can do a custom security policy. And you can see there on the right, you can still enable SSL v3. I strongly recommend that you not enable SSL v3, but if you have a business need to do it, you can still do it. Another issue that we've often run into with TLS implementations is they'll tell you that the connection was encrypted or not encrypted. But that's it. You get one bit. It's a flag that's on or off. And as you go to make changes, again, every time we've made changes to our TLS config, we've run into strange things. You need to dive deep here. And so this is a sample ELB log, and we've added the Cipher suite that was negotiated and the protocol version that was negotiated for that connection. These are fields that you can ignore until you need them, but then when you need them, you really need them. Do your crypto implementations log this stuff? You want them to. So let's switch gears a bit. We've been talking about how the data in TLS gets encrypted. Let's talk about how the keys are agreed upon. This is another great paper. You should totally read it. It discloses two interesting attacks. The first is a downgrade attack on TLS that causes the server to negotiate export-grade crypto, basically trivially breakable crypto. It's an interesting attack. You should read the paper. The second one that we're going to talk about is an issue with the Diffie Hellman key agreement protocol. And I love the Diffie Hellman algorithm. It is amazingly simple, and the result is elegant. It's not a key exchange protocol. It's a key agreement algorithm. And so the key itself never goes on the wire. The analogy that's often used for Diffie Hellman is color mixing. In the real world, it's modular exponentiation, but here it's color mixing. And so there's a common set of parameters that Alice and Bob agree on. And these aren't secret. It's okay if attackers observe these parameters. In the paint mixing version, it's a color. In the real world, it's a set of numbers, including a very large prime. They're each going to pick a secret color. They never, ever tell anyone their secret color. They mix the common paint with their secret colors, obtaining two mixtures, and then they exchange the mixtures. And so this relies on the assumption that unmixing colors is hard. The real-world version relies on the assumption that the discrete log problem is hard. And so now Alice and Bob each have a mixture of the common paint and the other's color. They add their own color, and they wind up with a common color. And anyone that has observed this exchange has no idea what that common color is. In fact, as TLS is negotiated, this whole exchange is protected with an RSA key or something like that. Even if an attacker gets the private key, they write down this entire transaction, every single packet involved, gets the private key, decrypts the whole transaction, they still don't have it. It's a feature called perfect forward secrecy. Even if the key is broken at some point in the future, this transaction, this agreement of the key is still secure. So the logjam guys separated the discrete log problem into 4 stages. The first 3 stages are per prime. So for any given 1024-bit number, you have to do the first 3 stages. And then for every exchange using that prime, you have to do the 4th stage. And for export-grade 512-bit crypto, it was about 50 core years per prime, and then 35 core minutes per exchange. And this is all highly, highly parallelizable. The 35 core minutes worked out to about 70 seconds of wall clock time using a commodity server. At 768-bit, you're looking at about 40,000 core years. And you know, I'm not going to do that on my laptop, but that's academic organization kind of power. And for 1024-bit, you're looking at 45 million core years, which at current market prices, current on-demand EC2 prices, is about $18 billion. $18 billion to break a TLS connection is bad math for anyone, even nation-state actors. The problem was that until this paper was published, we did not think that it was a bad thing. We did not believe that it was unsafe to share primes. And so there are TLS implementations, there are SSH implementations, IPsec implementations that have hard-coded primes. There are primes that are in use on millions of servers, used for billions or hundreds of billions of connections. And $18 billion amortized across hundreds of billions of connections. The math there is starting to look not so bad. So the paper has some fascinating speculation. I'm not going to go into it. You absolutely should read it. But it's another example of a non-Boolean failure in crypto. Someone has to spend a lot of money. It's not going to be $18 billion. You're going to get some FPGAs or ASICs or something. It's still going to be a major investment. But then 30 core days per exchange. Right now, it's about $1 a core day in EC2. $30 a connection, like that's pretty good math. And so 1024-bit Diffie Hellman isn't looking so hot. This is a screenshot of SSL Labs. This is a website that you should all know and use. You can put a URL into it, it'll give you a grade and a couple of stats at the top, and then there's page after page after page of detailed information about how TLS is done at that site. You can point it at your ELBs, you can point it at your on-premise infrastructure, you can point it at your favorite sites on the internet, and you should. So I just got done telling you that the logjam paper showed that 1024-bit Diffie Hellman was inadvisable. SSL Labs has capped our grade at a B because we're using weak Diffie Hellman key exchange parameters. That's English for 1024-bit. And I'm up here telling you that we own TLS deeply and that we've got a team that's dedicated to this. So something doesn't line up here. The math doesn't work. And what's happening is that SSL Labs is trying to take a very complicated topic and boil it down to a single letter grade. And there's always going to be edge cases that don't fit, and we're one of them. In the edge case here, Java, older versions of Java, claim to support primes greater than 1024-bit. But again, they're lying. No one tested it. The code made it out into the world. The code is years old. It's actually been fixed in more modern versions of Java. And if you hand them a prime, a 2048-bit prime, the process crashes. And so it just doesn't work. This isn't good. And so we've done something that I think is awesome. In S3, remember our grade is capped at a B. Every time our web server process starts up, each thread creates a new prime. Turns out that creating primes is too expensive to do in line with the connection, but it's cheap enough that we can do during startup, and it's basically not measurable. So on each physical web server box, there's tens of primes in use. Across the entire fleet, there's tens of thousands of primes in use, and these primes are constantly being cycled as web service processes restart for deployments or whatever. And so now we're not amortizing hundreds of millions or hundreds of billions of connections across one prime. It's not down to one connection per prime, but it's not a large number of connections per prime. The math doesn't work out anymore. It's not worth it to spend $18 billion or a fraction of $18 billion to try and break one of these primes. And the other thing is, just like Nmap does OS fingerprinting remotely, we fingerprint that client hello that we get in. And we use what we know about the billions of client hellos that we've seen over the internet to understand what it is that's sending us that client hello and what its actual capabilities are compared to the capabilities that it advertises. And we alter our response based on that fingerprinting. So your browser won't even be offered DHE at S3. In fact, we can tell that SSL Labs is using a version of Java for their back end because they were offered DHE. And so, again, this is pretty deep alteration of how TLS works. And the only reason we get to do this is we've centralized. I love the fact that this is engineering. It's not math, it's not science. It doesn't matter if it's theoretically correct, it matters how it works in the real world. And we've got one team that does this. Again, at AWS scale, even at our scale, we have one team that does this. We've also centralized on our TLS implementations. We have very few approved TLS implementations. I assume everyone here knows about Heartbleed. Heartbleed was not a protocol bug. It was not a crypto bug. It was a straight-up implementation bug in OpenSSL. You want to have as few implementations as possible so that you have as few, 1, 2, 3 sets of bugs that you need to keep up with. So we're always looking to get rid of TLS implementations. And I'm wearing an AWS shirt. I'm speaking at an AWS conference. But honest truth, our favorite way to terminate TLS is with ELB and CloudFront. We delegate that problem to a service team that is dedicated to doing nothing but doing that. Signal to noise is our internal TLS implementation. The two features that I talked about, automatically generating primes on startup and fingerprinting the client hello, are coming to S2N soon. S2N was designed to be correct and simple and easy to understand. It happens to be fast, but that's completely a side effect. I keep telling you, crypto is not for amateurs, and here we are implementing our own TLS library. We did not do this casually. We put a tremendous amount of effort into it. We had multiple rounds of external crypto review, multiple penetration tests. We had a stunning number of engineers within the company review the code, and the research community has also taken an interest in it, and we've learned some stuff. We have an automated reasoning team, and they're also awesome. And we have a proof of the correctness of the HMAC in S to N that runs automatically every time code is committed. And it breaks the build if the proof doesn't succeed. So we're starting to formally prove the correctness tied in with the build pipeline of S to N. And we've got more proofs coming. We welcome your scrutiny, your feedback, and your code submissions, and we'd love to have you use it in your projects. So one more thing we need to talk about if we're talking about TLS. Every time you make a change, it's an opportunity for a failure. And the more frequently the change happens, the more likely it is that the change is automated, the tools for making the change are robust, and the failure modes are deeply understood. And as the changes become less and less frequent, as the interval between them grows, the odds of a failure when you have to make that change go up, and this doesn't get better until it's someone else's problem, and I'm living in a bunker in Montana. TLS certificates, one-year TLS certificates, are outages that can be scheduled a year in advance. The only thing worse than a one-year TLS certificate is a three-year TLS certificate. And the world is not ready for short-lived certificates. We've got the Amazon Certificate Manager. We actually tried to go for 24-hour certificates. It turns out there's all sorts of reasons why the CAs and the browsers, and it just doesn't work. And so we're stuck with one-year certificates. But even at 1 year, you need tools. You need really strong mechanisms. And an Outlook reminder to update the certificate is not a mechanism. And so this is why I'm so excited about the Certificate Manager and its integration with ELB and CloudFront, and there's more coming. There's an entire service team dedicated to making sure that your certificate is current and correctly deployed to production. We've been terminating TLS for a long time. Amazon's been on the internet for about 20 years now. AWS has not existed for 20 years. Our certificate manager has existed for way less than 20 years. We have really good TLS and certificate management tools internally, and we are centralizing on our public services. We are transferring the ownership of our internal certificate management tools to the ACM team. We are moving our TLS termination to things like ELB and CloudFront because there are service teams that are dedicated to them. Again, we want to do this once, we want to get it as right as we can, and we don't want to have to pay to do it twice. Let's abruptly switch gears. Let's talk about encryption at rest. So this is our recipe for decryption. It's the same recipe that we had earlier. And we actually want to follow the recipe in practice. So we've got some sort of computer. It's a client device. It's a phone. It's a server. We've got a storage media. The storage media is chock full of ciphertext. And we've got a key. That's great, but we're not amateurs, so we're going to put the key in some sort of key management system. We're going to talk to the storage system. We're going to ask it for ciphertext. It's going to give it to us. We're going to talk to the key management service. We're going to authenticate. It's going to authorize us. Some dance is going to happen, assuming it succeeds. We're going to get the key. Of course, the math is public. Anyone can get it. And using those ingredients, we can generate the plain text. So it's just following the recipe. I am a vintage 1970s human being. I'm a photographer, and this is what happens when you put your camera down and your coworkers pick it up. I was born in 1974, which makes me 42 years old, which my coworkers tell me is really old, but I'm actually thrilled about it because I can use 42 as an answer to serious questions. My life expectancy is about 83, which means I have even odds of being on this planet for about another 40 years. Information about me is going to be important to me for 40 years. And if that information leaks, I can't rotate my genome. It's hard enough to repair your credit or change your password, but if it's information about me, the human being, there's nothing I can do. So 40 years, that's a long time, especially in the world of computers, but time passes oddly in the world of computers. This is a vintage 1970s binary search tree. Back in the 70s, you could search one of these things in log n time. Inserts, deletes, log n time. After 40 years of research, 40 years of PhDs, you can search one of these things in log n time. If it was a good answer to your problem 40 years ago, it's probably a good answer to your problem today. It's an old data structure, but it hasn't aged a day. Here's a vintage 1970s encryption algorithm. Believe it or not, as far as I can tell, there's no logo for DES. This venerable mainstay of the computing era has no logo, but every vuln gets a logo these days. It's terrible. So when I was not yet walking, DES was published. It was very quickly approved and standardized. It was pretty broadly used. And it wasn't until 1992 that we started to see serious erosion. Differential cryptanalysis was invented. I don't know, maybe it already existed and one of us smart humans discovered it, but it's just theoretical attacks at this point. 2 to the 47 chosen plaintext. It's a completely infeasible attack in the real world, but it's not a perfect algorithm anymore. In 1998, deep crack, custom ASICs, $250,000, but they actually broke DES. And the breaks just keep coming faster and faster until finally the Copacabana system. At this point, the important thing isn't the 9 days, the important thing is the $10,000. Anyone that really wants to break DES can break DES. 31 years, and it went from standard, shiny, awesome, to broken. And I'm going to be around for another 40 years. I use this somewhat macabre example of my life expectancy as an example of data that has a long half-life. There's a lot of data out there that has a long half-life. And again, we believed that DES was secure, and our beliefs changed. So there's another recipe. And it's not that this was a Boolean failure. It's still $10,000 in 9 days. I'm sure those numbers have gotten better. Maybe you can crack DES using F1 instances and drive the price down. But if you were doing DES on the network, you had years to realize that doing DES on the network wasn't a good idea and to change. Data at rest is, by definition, written down. It's kept for years. It's backed up. You keep multiple copies of it because you don't want to lose it. It gets archived. So that DES packet that you sent in the 80s, it's probably okay. The DES hard drive that you lost control of in the 80s, it's now trivially decryptable. And so we all know that keys are sensitive, but when you're talking about storage at rest, ciphertext is sensitive too. The phrase, "it's okay, it's encrypted," is not okay. So with durable storage, with long-term storage, we have to obsess about protecting ciphertext. One way to do this, you don't want your ciphertext wandering around, you bring your ciphertext close. This is the model that's used by my laptop. The cable is that long, the drive is bolted to the machine, it's there inside of the sheet metal enclosure. It's a great response to this problem, but it limits the utility of the data. It can only be used by that one server. And still, in this world, you're issuing keys to clients. In the case of my laptop, I don't know how many of you read the news. Anyone still using Firefox today? There's a bad 0-day that just went public in Firefox. And I run Firefox on my laptop. Not today, but yesterday. I click on links in email, like I'm untrainable, and issuing crypto keys to me, that may not be the best decision. So another option, another way to cook this recipe is to have the clients be clueless. They're oblivious about the way the encryption is done. So you call out to the storage system. The storage system calls out to the key management system. It authenticates. Assuming it authenticates correctly, it gets a key. It uses the math that anyone can get. It generates the plaintext and returns it to the client. So the downside of the system is clear. The plaintext is moving around. But on the upside, the keys stay in the back end. If you're logged into your storage server surfing the internet using Firefox, we have a very different conversation to have. There are fewer storage servers. They're more constrained. They're easier to monitor. It's easier to detect anomalies. Your keys stay further away from the scary internet. So that's a huge advantage. This is often a good choice to make. And the fundamental difference is if we're talking about keys in the network, you perform a negotiation, you agree on a key. If someone forgets the key, throw the key away, negotiate again. Get a new key. Someone loses control of the key. You start seeing it pop up in places. Throw it away, negotiate again, get another key. They're effectively free. The keys have no value beyond the life of the connection, and the life of the connection can be terminated whenever you want. On disk, if you have a terabyte encrypted with a given key, re-encrypting that data is 2 terabytes of I/O. It's a terabyte of read and a terabyte of write, and 2 terabytes of crypto, of course. Terabyte's not a lot anymore. We don't talk about terabytes anymore at Amazon. So it's going to be very expensive to rotate. That leads to key wrapping. You're going to wrap the key. So it's not the key that's floating around, it's the wrapped key that's floating around. So if that key goes wandering, you can change the wrapper. And you can tell everyone, never unwrap the green key again, only ever unwrap the blue key. And as long as your wrapping protocol is good, we believe our wrapping protocol is secure, you're good. You haven't actually lost control of your key. So this is complicated. So we're going to wind up centralizing this on some sort of key management system. Key management systems are a side effect of long-term durable crypto. We moved the complexity into one place in the hopes that we'll get it right. Maybe you still move the key over the network while it's wrapped to provide extra protection. But in the end, wherever you're using that key has to be in memory, in plain text, for as long as that client needs that data. That key is exposed in plain text somewhere for as long as that data is needed. So keys are not just sensitive, they're long-term sensitive. Mistakes here can be difficult and expensive or even impossible to recover from. And so is the ciphertext. And so our best practice is to treat your data encrypted at rest as if it were clear text. It's still encrypted. You've still got the benefits of encryption, but you obsess about protecting it as if it were clear text. I cannot find an attribution for this image. It's all over the internet, but I absolutely love it. You're welcome to steal it from me. Bad crypto is worse than no crypto. If you open a file and it's full of credit card numbers or social security numbers or whatever it is that's sensitive to you, you will immediately say, oh my, that file is sensitive, and you will treat it correctly. If you open a file and it's full of garbage, it's encrypted, I'm safe. Even if it's encrypted with ROT13, your eye can't decode that. And so it's going to lull you into a false sense of security. It's going to fool you into allowing things to happen to that encrypted data that shouldn't happen to it. And so when we find bad security controls, bad crypto controls, and we actively hunt them down, we either fix them or we turn them off. I would rather the data be explicitly clear text than poorly encrypted. It's cheaper, like you're not paying the CPU cycles, but most importantly, you realistically understand what that data is and you treat it appropriately. The problem here is that good crypto controls can turn into bad crypto controls overnight. And so again, you've got to stay on top of this stuff. So I've been talking about a whole bunch of stuff. This is how we do it in S3. We've got KMS, we've got S3, and we've got something that's supposed to be the Bodo AWS SDK. And we've got web servers in S3. I'm not disclosing any secrets here. This is the only part of the S3 service that's externally visible. There's a storage backend. You can't see this, but I assure you that it exists. It does all sorts of storage stuff. A customer request comes in. Let's say this is me. I want to process one of my pictures. Maybe it's the picture that my coworker shot of me while I wasn't paying attention. The web server is going to call out to the storage backend, and it's going to assemble all of the pieces that it needs in order to assemble the ciphertext. No single host in the storage backend had the ciphertext. The ciphertext only exists on the web server. It's also going to call out to the storage backend and get the wrapped key. Then the S3 web server is going to call out to KMS, the AWS Key Management Service, on behalf of the calling user. So we don't have rights to call KMS and unwrap keys unless there's a customer API call present. And so we're going to negotiate with KMS, and we're going to say, no, it's Eric. Here's proof that Eric is calling. And then we're going to do a second authorization. We're going to say, is Eric allowed to unwrap this key? And assuming that that all succeeds, KMS returns the unwrapped key to S3, at which point S3 can forget the wrapped key. The web server forgets the wrapped key. We can now use the math that's commonly available, plus the key, plus the ciphertext, generate the plaintext, and then we can forget the ciphertext and the key. The key's gone from memory, the ciphertext is gone from memory. At this point, there's no single host in S3 that has the ciphertext on it. And then we can return the plaintext to the customer. Now, to do this right, the customer has to call us over TLS. If the customer calls us over TLS, we'll return the plaintext over TLS. This thing is encrypted end to end, and that S3 web server can now forget the plaintext. So that server is returned to its initial state. The ciphertext doesn't exist on any single host anywhere in the system. The plaintext doesn't exist anywhere in the system. The cleartext key doesn't exist anywhere in the system. This is how we do AWS, KMS, encryption in S3. So encryption is hard. And I don't mean it's hard for us or hard for you. I mean it's hard for human beings as a species. We're young here. We haven't figured this out. We are amateurs. The answers here aren't clear. They change regularly. And getting this stuff right takes experts. It takes time. The math of cryptography matures over a course of years. And then the engineering kicks in. It has to actually work in the real world with the code that's deployed. And there's no point in doing any of this if it doesn't meet your business needs. Like, I'm a security guy. It's my job to make sure that we do things right. But if I make sure that we do things right and it results in us shutting down the business or losing a large swath of customers, I'm not actually doing things right. It has to work in the real world. Encryption is expensive. Even at AWS, even at our scale, we've got one team that does this. We've centralized. We've made sure that we've got a set of experts. We've made sure that they're deeply invested in the community, they're participating in the discussion. And you can't just set these things and forget them. Remember that bathtub curve of change? Crypto rarely breaks overnight. It's a process of erosion. And so it lasts long enough that you think, I'm done. Like, I did a good job. I'm meeting the NIST standards. I'm using only Sweet B algorithms. Like, I'm good. And you forget about it. And people move on, and that system, like the most dangerous software systems in the world are software systems that are done. If the software system is still under active development and you've got a team of developers that know the code base and they know what's going on and they can fix it rapidly, that's a good place to be. If you've got a system that's been in operations mode, it's just on life support, they did too good a job building it and it never breaks and it's just sitting there humming along and you've got one guy that puts a quarter in the machine once a day so that the electric bill doesn't run out. Those are the systems where you're still using MD5 and RC4. And changing those systems is hard, it's expensive, and it's easy to defer that maintenance. Just punt it to future you. Like, future you can't get back at current you. Make them deal with it. And it's so easy to do that until it isn't, until it's way too expensive. But still, it's worth it. It's this awesome control. It's this magical thing that allows you to use clock cycles to turn valuable data into undistinguishable noise. And so we use encryption broadly. We encourage you to use encryption broadly. But we encourage you to use encryption broadly and own it deeply and understand what it is that the encryption is actually buying you and continue to own it through the life of the system. I'm going to close with a quote from one of the greatest computer scientists of all time, Yogi Berra. I believe that attribution is not accurate, but this quote sums up the way I think about cryptography. The real world is much grungier, much more malevolent than any model can capture. It doesn't matter what the simulation showed. It doesn't matter if you have a proof that it should be functional. All that matters is if it works in the real world, if it actually achieves your business goals, if it actually achieves your security goals. This actually sums up pretty much my entire career at Amazon. It doesn't matter how well it should work. It doesn't matter anything except how well it's accepted in the marketplace. That's the core difference between science and engineering, and I love being an engineer. It's why I come to work in the morning. Thank you.